Now, as an introduction, a transistor is a semiconductor device used to amplify or switch electronic signal and electrical power. So it has two functions. We can use transistor as amplifier and a switch. It is composed of semiconductor materials, usually with at least 3 terminals for connection. Now here, we have what you call a PNP transistor. This is the physical construction, PNP transistor. So this is the positive side, negative side, and another positive side. This is called the emitter, the base, and collector for PNP. It can also be an NPN, where emitter here is the N. This is base, now it's P, and collector, which is N. And this PNP is a back-to-back diode, as you can see from this figure, and also NPN also is a back-to-back diode. As you can see, this diode is the negative of the diode. The positive of the diode are together, positive of the diode are together, and we have negative. So this one here is NPN. Okay. Now this is one example of the diode. Here is BC548. Okay, terminal number one is the collector, base, and number 2 is base, number 3 is emitter. And here is the symbol for an NPN transistor, collector base emitter, and PNP transistor, collector base emitter. I'm going to discuss to you also in this slide what are the difference between the collector base and emitter, and also in the construction, right? In either case, the center layer form the base, the external layers are emitter. The relationship between the voltages and the current associated with the bipolar junction transistor under bias operation condition determines its performance, right? So it is the voltage current relationship in the transistor itself determines its operation, and we can control that. We can modify the relationship using the process called biasing, which we are going to discuss later. And previously in our diode topic, I discussed to you about the doping process, right? And now I'm going to show you. We talk about the construction of the transistor. Here with the emitter. The emitter is actually larger than the base, with a ratio of around 150:1. The emitter and the collector are almost the same size, the same dimension. As you can see here, 0.150, 0.001, and 0.150. So it is the ratio of the width is 150:1. This will also affect the resistance, the conductivity of the material. The conductivity of the material by limiting the number of prick areas. Of course, if the width is less, the cross-sectional area is less, the volume is less, so it can control the number of prick areas. Now, this one very important. In order to operate the transistor, here are the conditions. The emitter and base must be forward bias, right? The emitter and base must be forward bias. The base collector must be reverse bias. Again, emitter, base must be forward bias, and the collector base must be reverse bias, so that your transistor should operate, right? As you can see here on this example, we have positive here, negative here, and positive connected to P and negative connected to N. That means this side is forward bias. And here we have negative side connected to P and positive side connected to N. This is a reverse bias condition. And also here we have an NPN. For NPN, we have forward bias also here. This negative connected to negative, and the positive connected to positive here, forward bias. And here we have negative connected to positive and positive connected to negative. It is reverse bias. So these conditions must be observed. Again, I want to highlight that these conditions must be observed when you are connecting the transistor in your circuit. Transistor amplifier amplifies an ACC input signal that alternates between some positive value and corresponding value. This can be done through proper biasing, and biasing is very important in amplifier. It establishes correct operating point of the transistor amplifier, right? So, as just an example, if this is your signal amplifier, amplify means the signal must be, the output must be larger than the original signal. If your signal is here, let's say we have here, as an example, 10 millivolt, right? And then here in an output, your expected output will be an inverting output, but with a large amplitude. Let's say here you have 1 volt. Let's say 1 volt output, peak to peak, right? Peak to peak means from this peak up to this peak, positive peak and negative peak. That means peak to peak value, BPP. Okay, BPP. Okay. Now, let's go to next slides. Biasing determines the voltage and current associated with bipolar transistor. Now, if you look at this is our transistor, and these are the resistors to bias, that resistors to control the biasing of the transistor, right? So when look at this figure here, it is said to be in saturation region when the transistor is switched fully on, right? When the transistor is switched fully on, as I've said earlier, we can use a transistor as a switch. When you say as a switch, it can operate on and off, right? This is the switch function. This is the switch function. So when this is saturation region, which is this one here, saturation region, the transistor is fully on because we have a very large current here, large current. At cutoff region, the transistor is in off, right? What is the condition when the transistor is in off mode? When BCE is equal to BCC. When BCE is equal to BCC, then the transistor is in off mode. In other way, for saturation, when what? When BCE is equal to 0. Where is BCE? Where is BCE? Where can you find BCE? From this figure. BCE is this point, because this is collector. Why this? This is the collector. Okay. This is your collector. This is your base. This is your emitter E. So the voltage between this is BCE. If this is equal to 0, then we can say that your transistor is in on mode or saturation region. Active region. This is what, if we want to use the transistor as an amplifier, it should operate as in active region. And this Q point is used when transistor as an amplifier device, and this is operated in active region, and of the input characteristics. There will be a minimum distortion at Q point. So this is the Q point here, right? This is the Q point. And if you are designing your transistor, it should be, you have to consider BCE should be equal to 1/2 BCC, right? BCE is equal to 1/2 BCC. If you're, let's say, for example, your BCC here is 15 volts. So then you have to design BCE must be around 7.5 volts. Okay? And here, by the way, sometimes you were not able to put it in the you are given some example. These resistances are given. These resistances, analyze the circuit, right? Analyze the circuit and find out where is the Q point of the transistor. Sometimes the Q point of the transistor is on this point or in this point, or sometimes after calculation you find out in this point within the load, within the DC load line. Within the DC load line, it means that at these points the transistor is still used as an amplifier because it is still in the active region. But the best location of the Q point is on the center, here, where BCE is equal to 1/2 BCC. But if you go here, beyond this, around this area, right? Or at this area, it is now operating as a switch, on and off. So the region of operation of transistor, let us have a review. If it is said to be an active region, if the voltage BCE is between 0 and the voltage BCC. So between 0 and the voltage BCC, around, maybe we can say within this region, right? Within this region, we can say that it is in active mode. Okay? So cutoff region, when BCE is nearly or about equal to BCC. BCE equal to BCC, it is in cutoff region. And saturation region, BCE is as low as 0 volts, right? So that's why we have IC, it's in on position. So this one will be ons. This is in off, right? The switch is off. So if you use transistor as a switch, you need to operate the BJT in cutoff and saturation, and use it as a amplification for an amplification purpose. You have to operate this as an active region. Now let us have an example. You are giving this problem. Calculate the R1, R2, RE to set the Q point of the amplifier. So now you have BCC. Of course, BCC should be given. BCC is given, assuming BCC is given. RC is given. Beta is given. BRE, right? BRE is given. Now, to calculate, we need to calculate RC is given. This is given. BRE is given. So, if it is E, so the voltage across here, BRE, is given. And also the beta of the transistor, right? Now, determine ICQ. This is the equation. ICQ is BCC. ICQ here, let's ICQ is equal to BCC minus BCEQ, right? Minus BRE, right? So if we have BCC minus BCEQ minus BRE, what is this voltage? This is voltage is equal to BC, right? This is BC, this voltage, BC. So if we know BC divided by RC, you can know the ICQ, okay? So you can know the value, this current ICQ here you can calculate, right? So ICQ is equal to BC all over RC, right? And BC you can determine with this, BCC minus BCEQ minus RE. Okay, let me just make it clear. Erase all. Okay, so BC will be equal to BCC minus this voltage. This is BCE minus BCE minus this voltage BRE minus BRE, or we can say BE, right? So what is the remaining voltage here? So it will, this is BC, the voltage between this, right? The voltage between BC, we can say BRC, sorry. We can say this is BRC. So that we will not be confused. So this is BRC, right? Okay, so what is ICQ now? ICQ will be BRC all over RC, okay? Let me just erase this portion. I need this space. Okay, now let us now calculate the value of R2. The value of R2, we need to calculate R2 here. Let's have a portion here. This current flowing here is I1. This current flowing here is I2. Now, of course, I2 is equal to this voltage, B2 over I2, right? What is B2 equal to? B2, this is B2. B2 will be equal to what? We have here silicon, it means 0.7. We have here 0.7 plus BRE. Okay, plus BRE. So we can calculate I2, right? I2 is equal to B2 all over R2, right? Then we can calculate R2 if we know what is the value of I2. But as a general rule, what is I2? I2, the current flowing through R2, is 10 times IB, right? 10 times IB. Do you have the value of IB? Do you have the value of IB? IB is equal to ICQ all over beta. Is beta is given? Beta is given here. So you can determine, you can have value of IB. So now you will have complete this equation. BRE plus 0.7 over 10 IB. 10 times. This is the general rule. Now let us calculate R1. For R1, the current I1 flowing to R1 resistor is, in the voltage divider must be 11 times. 11 times the value of the base current. Why 11 times? Because this one here is 10 times, IR2 is 10 times, plus this one. So 10 plus 1, 11. So 11 IB. So it will be equal to what? What is the value of B1? Let us calculate B1 from here. B1 is actually BCC. What is B1 here? This is the voltage across here, right? This is B1. BCC minus what? BBE plus BRE. Okay? BBE plus BRE. This is B1, which is this. Okay? Then we can calculate R1. Then IB is the current I1 is 11 IB. So you can calculate the value of R1. So now you will have the value of R1, R2, RC. You can calculate also the value of RE, right? Because how to calculate the value of RE? You can now have RE is equal to BRE over IE, right? But what is IE? Okay, BRE is equal to IC plus IB, right? So you can calculate the BRE. Okay? Now, let us now start with the biasing analysis. We have the value of R1, we have the value of R2, RC, and RE. Let's say, for example, beta is 250. Using the voltage division rule, it is we can approximate that this is series, right? This portion will take the voltage division rule here. Why we considered it a series? Because this base is very, very small compared to the currents flowing here, right? So taking the voltage division rule, we can say BR2, the voltage across R2 is equal to BCC times R2 over R1 plus R2, right? So we have BTH equal to 4.78. So the voltage here is equal to 4.78. And what will be our RTH? Between from this point, RTH, we can say that they are in, when we consider, to get the RTH, we consider them as in parallel. We cannot neglect this IB here. We consider them as in parallel, R1 and R2. We will have R1 parallel with R1, R2 over R1 plus R2. R1 multiplied by R2 over R1 plus R2, we will get 15K, right? RTH is 15,000, okay? So we will have BTH, RTH, okay? BTH, RTH, we can take the KBL here. What is the KBL? Minus BTH plus RTH IB plus BBE plus IERE will be equal to 0. From this equation, we can calculate, simplify, substitute the value of beta. We can get the value of IB, right? We can get the value of IB after calculation. This IBQ, this is the IBQ 7.19, right? So if we know the beta, we can also calculate the IC and IE using these relationships here. Okay, we can determine IC IB. Now, what will be our BRC? The voltage across here, RC. Voltage across here will be, we have IC multiplied by 3.3K, which is this one. This IC here, 5.91. So we can calculate BC. What's BC? This is BC, the voltage here with respect to the graph. BC is equal to 15 minus 5.91, 9.09. And BE will be equal to 1.8. We have 1.8, right? BE is IE multiplied by RE. So 1.8 multiplied 3.96. 1.8 multiplied by 2.2K, 3.96. And we have BB is, so this will be 3.96. Sorry, this one 3.96. Sorry, it's correct. 3.96 plus 0.7, 4.66. Okay, 4.66. So we have BCEQ will be BC minus BE will be 9.9 minus 3.96, 5.13, right? 5.13. And we can check. Here, there is this actually is our Q point here. This is around 5.13. Here is 5.13 volts. So, this point, our IB is 7.19. We have 7.19. This is our IB, right? Then, the value of IC may be around 1.79. This IC here, 1.79 milli, right? From here. This is how you plot the Q point from this figure, right? This is IC. And what's the value again of this IC? IC saturated. IC saturated, let me highlight this one. IC saturated will be BCC over RE plus RC, right? Because we assume here that BCE is equal to 0. This IC is the saturated, IC saturated. This is our IC, ICQ, but this is our IC saturated, right? What is this point? When you want to plot the load line, here, what is IC here? You calculate. Let me erase it again, make it clear. It has been, if you want to plot your load line, you consider this equation. Okay, BCC over RE plus RC, substitute the value, you get 2.72. So this will be your IC saturation. Go to the other side when BC is equal to BCC, right? This is 15. Okay, then you can plot straight line between this point and this one here. You will have the DC load line, and along the DC load line, the Q point must be there. So this is your Q point. Okay, along the DC load line, the Q point must be there. So this one is used to draw your DC load line, this relationship, if you want to draw your DC load line. Now, let's say we change the transistor with another value, with another beta, which is 80, right? A transistor was, the transistor beta is 80 only. Again, we apply the same scenario. Say, the IBQ will change, right? Same value of BTH here, RTH here, and just substitute this beta, 80. We'll have 21.12. Calculate ICQ and IE. Then you can also now see the changes. We will have here BRC, the BRC here, and you can have BC. After you calculate BRC, you can calculate BC, and the objective is to determine BCE, right? BC here, and here is BE. Okay. After that, you calculate the BCEQ. BC minus BE 5.66. So this is also here around here, so it's go down a little bit. So IB here, it's no longer, so this is wrong. It should be 21.12 micro. 21.12. Oh, the pen is very thick. I don't know how to make it thicker. So this one is wrong. It should be 21.12. So this is one, it should be 21.12 microampere, right? This is your IB. And look at your ICQ, it's a little bit go down here. This is 1.69. Okay? And of course, this is, you know how to plot this from the previous example. Now, in your experiment, you will assemble the circuit. This R1 is given to you, and determine the BC. If you want to determine what is the required here, BB, BE, BC. BC here, just use the multimeter to put it here and connect here with respect to the ground. You will get BC. If I want BE, this one here, I can connect here and connect to the ground. I will have BE. And what about BB? BB, of course, you have to put here with respect to the ground. Very simple, right? So now if you want to change the current, IC, you just put here, put it in ammeter mode, ammeter. You can just put here, what's the current? And here, just look at, I open also here. You have to put here, and you have to put here, right? Remember, this now is open. This one here is open now, open. I need to open. This one here also is open. And IB, you have to put here positive. You have to put here negative. As you can see here, you need to open, right? To measure the current. Now, in your experiment also, you are required to determine the transconductance. Transconductance simply is the ratio of IC with respect to BT. BT is the thermal voltage of the transistor, and at room temperature we can consider this around 26 millivolts, right? Okay, and thermal voltage is actually arises from the junction at the temperature. We have this relationship between the electron charge, right? Electron charge and the we have K multiplied by T. So BT is equal to KT over Q. So if you want to calculate the where Q here is the 1.062, the electron charge, and K is the Boltzmann constant, right? When you want to calculate BT at different temperature, right? Let's say here at room temperature, here is around 27 degrees. Let's say it should be in Kelvin, by the way. Kelvin temperature. Here is in Kelvin. Let's say at 400 degree Kelvin. What is the threshold voltage? Some questions like this, right? You can use this formula. So again, this is equivalent to BT is equal to KT over Q. So now we also have some other technique, which is approximation technique. In approximation method, we can consider that IC is, since IC is almost equal to IE, we can approximate this equation, this relationship, IC equal to IE. Then we can have BCE directly is equal to BCC multiplied by IC, or you can use this as IE, right? RC plus RE. Okay, this is what? This is approximate method. Approximate only. So we have here BE, IE, RE, right? If BE is given, you can immediately calculate RE as BE over RE. Then use this value in this equation. You can now immediately determine BCE, so you can know your you can plot your load line, right? You can plot your load line. Let's say this is the Q, this one here, using this equation, equation 1. Yeah, this is used from equation 1. You can see here, this is BCC equal to BCE, and here ICQ is equal to, I give you the BC here, the equation. These are the other equations that you can use. And remember, I2 is equal to 11 times IB. I2 is 10 times IB, and I1 is 11 times IB. Now, these are some examples of transistor. This is what we are going to use in our experiment, BC107. This is the pin out emitter-based collector, right? Or in this also, sometimes we are using 3904. Okay. Now, we have a transistor tester actually here, and here is HF. We test the transistor. Look at this 3 terminal. Okay, this 3 terminal, you can say here example, the red is base. It will give you the green emitter, blue is collector. It will tell you what is that point. And also this tester component analyzer, it will tell you the HFE. What is this HFE? HFE is the beta. Okay? HFE is the beta of the transistor.